In this video, I'll show you how to solve the ALEKS problem called Distinguishing Accuracy and Precision. This problem is going to give you 4 different measurements for a particular number. It's also going to give you the actual value of the number, and it wants you to identify which one of these measurements is the most accurate and which one is the most precise. Let's start by distinguishing accuracy from precision. The most accurate number is the one that is, I guess for lack of better terms, the one that is the most right, the one that is closest to the actual value, in this case, which is 56.0. The most precise measurement is going to be measurements that have the least amount of uncertainty. They don't have to be right. They just have to have the least amount of uncertainty. So sometimes the most precise measurement is not the most accurate. Don't assume that you're going to be checking both most accurate and most precise for any one of these. So let's go with the accuracy first, the number that is the most right, compared to the value of 56 meters, which is the correct value. And I'm going to start from the bottom and work my way up. So this particular measurement of 55 compared to 56, this had an error, or it was off by 1 meter. I'm just going to write that down. Actually, I'll write it down right here. This was off by 1 meter. I'm actually going to leave the unit off. I'm just going to say it was off by 1. This number right here said that their measurement was anywhere from 54 minus 0.2 up to 54 plus 0.2. So this would be 53.8 up to 54.2. That was their measurement. 54 plus or minus 0.2, and that's pretty far off from 56. So we'll go with the high-end measurement that they got, and they were off by 1.8 meters, which is not great. And this person said 60 meters plus or minus 0.3% of 60. So let's see what that is. 60 times, no, not 0.3, 3%. Oh, that's even worse. 60 times 3 divided by 100 because it's a percent. So that's an error, I'm going to write it like this, of 1.8. So this measurement was 60 meters plus or minus 1.8. On the low end, well, we'll write the range down. 60 minus 1.8 would be 58.2. So this was ranging from 58.2 to 61.8. That's even further off from 56. So their error on the low end, they were 2.2 units away from the correct number. That's pretty bad. And then this one, their measurement said that they were between 57.6 and 58.4. So again, like the closest that they got, they were 1.6 meters away from the actual value. So this number here is the one that was the most accurate. It was just based off of these numbers right here. The measurement of 55, it was the one that it was the most right. They came closest to the actual value of 56. Now let's take a look at uncertainty. Again, don't assume that the most correct number is the one that has the least amount of uncertainty. Sometimes that's the case, sometimes it's not the case. For uncertainty, I'm going to start from the bottom again because this one is the easiest. If we're just given a number and there isn't any kind of error communicated in the number, then the uncertainty is expressed by the significant figures in the number. The last digit, the last significant figure is measuring the uncertainty of the measurement. So for this particular number, 55, the last significant figure is in the 1 position. So this has an uncertainty of 1 meter. Just to try to kind of give you a little bit more examples with that, if this was the measurement that we had, 55.0 meters, then the uncertainty for that would be 0.1 because that would be our last sig fig. If we had 50 meters as our measurement, this would be the last sig fig. Going from right to left is what I mean by last. So this would be our last sig fig, and this would have an uncertainty of 10. So if you're looking at something in this format, you're just going to go with the last sig fig as your guideline for the uncertainty. For this one, the uncertainty has been expressed for us. The uncertainty is this plus or minus 0.2. So the uncertainty here is 0.2. For this one, the uncertainty was communicated by the 3% of 60. We calculated 3% of 60. It was 1.8. That's the uncertainty there. And then for this one, the number that has a range like that, this one's a little bit trickier to calculate the uncertainty. What we're going to do in this case is that we are going to assume, so the numbers ranged from 57.6 to 58.4, and they're saying they're somewhere in this range. What we're going to do is find the midpoint of 57.6 and 58.4. I'm going to do that by subtracting 58.4 minus 57.6. So they are 0.8 units apart, so that means the midpoint is 58. I probably should have been able to do that in my head. That's the midpoint of these two numbers, and the difference between these numbers and the midpoint is 0.4. And we're going to assume that that's the uncertainty with this particular measurement. So they think that it's 0.4, it's plus or minus 0.4 away from 58. So 0.4 is the uncertainty for that team A. And what we're looking for here is the number that has the least, or the measurement that has the least amount of uncertainty. The least amount of uncertainty that we found is this right here, 0.2. That's the smallest amount of uncertainty. This is the greatest amount of uncertainty.